Test, test. Okay, seems good.
Introduce yourself.
Okay, hi, I'm Daniel. I'm from Aarhus University. I'm going to be talking today about a modal deconstruction of Loeb induction. So the starting point for this work is the observation that recursive equations are sort of the bedrock for what we do with denotational semantics of programming languages. They're sort of inevitable and they crop up in most language features. And I've been sort of envious of everyone here having formalized claims in their papers, so I decided to prove this inside of a type theory. Yes, so here is my very short formalized proof that recursive equations are quite useful. But unfortunately, this mostly just leads to the conclusion that recursive equations and dependent type theory, there's something fundamentally in tension. Yes, they're simply unsound if we add them naively. But this is irritating because we do want to use recursive equations when modeling things. So there's sort of this cottage industry of constructing limited forms of recursion that we can safely add to dependent type theory. And I want to focus on one of those, and that's guarded recursion. So the sort of thesis of guarded recursion is that recursion is okay to add to dependent type theory, it's sound, provided that we don't have any loops that just spin while producing no output. That prior to making a recursive call, we at least do some sort of work. So we have to crystallize what that means, what it means to do work. And we do that using a modal operator, which is written with this black triangle later. The idea is that later A is supposed to be basically the same thing as A, but you can't get a hold of those values until you do some work. You have to take a step. And the version of the fixed point combinator, which is now sound, is called Loeb induction. And it says that if you have a guarded function, a function that goes later A to A, then you can get a unique fixed point of that. So that's later A to A gives A. And the thing to notice here is that now our prior bad proof is ruled out because we're immediately returning proof, but it has the wrong type. It's supposed to have the type such and such, but it doesn't. It has the type later such and such, and these are not the same thing. And there's quite a lot of prior work on guarded recursion, and it's sort of focusing on different ways to sort of slice and dice the integration of later and Loeb induction into dependent type theory. So before proceeding to what we're doing, I wanted to give 30 seconds of introduction to what guarded recursion is supposed to be doing. So the intended model of guarded recursion is something like proof-relevant step indexing. This is done using a pre-sheaf model of type theory in pre-sheaves on omega. But if this is not such a comfortable concept, then you can think of types as being families of sets indexed by the natural numbers. And we want to think of them as flowing towards zero with time evolving towards zero, counting down. The idea is that you don't have a value of x, you have a value of x at stage n. And then crucially, the action of the later modality of the black triangle on these families of sets is to sort of shift everything up. So what was stage 1, or stage 0 now becomes stage 1, what was stage 1 becomes stage 2, and the 0th stage now gets filled in with the trivial set, with one element. And now Loeb induction is sort of justified just by inducting on the step. So induction on the natural numbers in the model yields Loeb induction in the theory. Okay. Yes, look, it's the single object set. All right. So, are we done? Not quite. So the thing is, later as a modality doesn't like to come by itself. It works best with this whole collection of additional type operators that help us sort of refine the behavior of the operation. And moreover, just because later and Loeb induction are sound, this doesn't mean that we get a satisfactory type theory out of them. We want the usual battery of meta-theorems. We would like this to have decidable type checking, to satisfy canonicity, and moreover, just to be implementable in some way. Okay? And so into this problem, I propose Gatsby, which is a version of guarded dependent type theory. And the idea is to simply add a lot more modalities than later, but to then remove Loeb induction, which turns out to be a rather problematic combinator we'll see later. So the idea is that we add more modalities, and we add one basic reasoning principle about that one of these modalities, and from it we derive Loeb induction. Okay. So about all those modalities. So here's the pictorial representation of all of the modalities that are occurring in Gatsby. I've rendered them as a sort of directed graph here, but I want you to think of them as like a category. So these are the generating morphisms of some category. And in particular, there are actually two very distinct classes of types inside of Gatsby. We have T and S. We call these modes in the paper. And the idea is that types at mode T, those are guarded types. Those are the ones that want to talk about Loeb induction, that later acts on, all that stuff. But then alongside them, separately, we have mode S. And these are meant to be just ordinary standard types. No guarded recursion. This is where you prove the theorem that you want other people who don't like guarded recursion to be. Okay. And we have a lot more modalities in this system. So we have L here, which goes from guarded types to guarded types. And this is going to be the encoding in this category of later. But alongside later, we also have earlier, which goes from guarded types to guarded types. And then we have a whole mess of operations which bridge the gap between standard types and guarded types. And these are modalities that encode operations like, given a standard type, give me back the guarded type, which is just constant. It doesn't change as time flows. And then I also have the ability to take a guarded type and give me back the corresponding standard type, which is like the stage 0 version of the type. Or I could ask for the stage infinity version of the type. And actually, the novel addition that Gatsby provides is this modality top, which goes from standard types to standard types. And confusingly, all this modality is meant to represent is the operation which sends every type to the unit. This is a bit trivial, but we'll come back to later why this is actually an interesting thing to add to the theory. Yeah? And just to say, there are equations on this category which describes the morphisms, and these are realized in the type theory by sort of equivalences between the modal types. So we write the modal types with these angle brackets and then the letter, just to have some sort of uniform notation. And so the equation that says that earlier after later is the identity boils down in the type theory to an equivalence of types that says earlier later A is the same thing as A. All right. And the good news is that there's been a lot of work on modal-dependent type theory, and even modal-dependent homotopy theory, which is something that will be, or homotopy type theory, which is something that we'll be really capitalizing on in this talk. So it's relatively easy to get an off-the-shelf type theory that has all of these modalities and all of these operations more or less for free. All right. So that's the good news. The bad news is that this doesn't actually help us at all in trying to get Loeb induction. You can't just add more laters and more like modal operators to type theory and somehow get Loeb induction out, because modalities are too formal. They basically, you can't tell the difference inside the type system between later A and just A. They're distinct in the syntax, but you have models of the theory where every modality is the identity function. So you're not going to be able to get Loeb induction out of these things. And actually, the situation is much worse than just that. Because if we add Loeb induction as a constant, then we have to decide whether or not we want it to compute, to unfold. And if we have it unfold, this is sound, but it will violate decidability of type checking. And if we don't let it unfold, well, then we lose canonicity. It's just going to be stuck. It's not going to compute anymore. So neither of these two extremes are really that satisfying. We need to somehow strike a middle ground between having it unfold all the time and unfold none of the time. And so prior work on this comes in the form of clocked cubical type theory. You have a fancier later modality, and you use that fanciness to sort of selectively unfold Loeb induction so that it kind of only computes at the top level. But I want to propose a rather different solution. I would rather just not have Loeb induction in the theory and to get it out of somewhere else. So let me move the goalposts, and let's talk about a different proposition, which I'm going to call bomb. So it's written with this font awesome bomb symbol. Okay, so first, advice on reading this proposition, yeah? So the two vertical bars, that's propositional truncation from homotopy type theory. So the propositional truncation of a sigma, it kind of behaves like an existential. So you should read this as, there exists some natural number such that later to the n false is true. And the sort of intuition is there are n steps left before things are trivial. And this is true in our intended model. It's not completely obvious, but it turns out that when we're proving elements of an existential in the model, we get to pick different witnesses at different stages. And while there's not a single number for which later to the n false is true, at every stage, there is a number for which it is true. It's just differing between the stages. At stage n, it's n plus 1. All right. And so the intuition for bomb that I want us to carry forward is that it's some sort of like doomsday proposition. It is the very pessimistic belief that the entire theory is about to collapse. We just don't know when yet. Okay? So the idea is that when bomb is true, then eventually everything is going to fall apart at some point that we don't know yet. And the reason to consider this is that it turns out that if BOM holds, then Loeb induction is just provable, right? So guarded fixed points are unique when they exist. And so if we want to prove that Loeb induction is definable, it suffices to show that every guarded function has a unique fixed point. And in homotopy type theory, that type, there exists a unique blah, 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 that's always a proposition. So when we're proving it, when we're trying to construct a map from BOM to that proposition, we're allowed to forget the propositional truncation. And now suddenly we have an actual concrete natural number such that later to the n false is true. And so now we can just perform induction like we would in the model, actually reduce to the case where everything collapses and then inductively build back up. So this is our first use of univalence in the form of Hoth's more semantic notion of proposition that allows us to show that there exists a unique blah, blah, blah is actually a prop. This would also work in extensional type theory. We'll see a more impressive use of Hoth in a moment. Okay, so now we just need BOM to be true, yes? And the issue is that if we just postulate BOM, then we're in exactly the same position we were before, right? We can eliminate the cut and we have Loeb induction, and that's going to make type checking undecidable. However, it would suffice if we can find a collection of types which believe BOM is true without us having to postulate it. So these are types A, such that A is equivalent to BOM implies A. We say these types are accessible. And these are the types that when you're trying to prove A, you're allowed to pull a proof of BOM out of your goal and just use it. And so in particular, if A is accessible, then Loeb induction is definable for A within the theory. We don't need to add it because we're trying to prove an A, so we'll just pull the BOM out of the A and then use that to construct Loeb induction. Okay? Not everything is accessible. If everything was accessible, BOM would be accessible, and then BOM would be true, and then we'd be toast. But it turns out that a lot of things happen to be accessible. This is kind of the happy coincidence of this talk. So we can take a result off the shelf from the literature on homotopy type theory and conclude that accessible types are closed under pi, they're closed under sigma, they're closed under equality, the unit, and in particular, the universe. So a crucial consequence of univalence is that the universe of accessible types, the subtype of the universe spanned by accessible types, is itself accessible. This is great, but we still have no non-trivial base types. And getting non-trivial base types is where we require this fancy new rule. Yeah? So now we return to that trivial modality that I mentioned way at the beginning, this top which goes from standard types to standard types. We're going to add one new rule to our modal type theory. And the consequence of this rule is that the modal type top A is always trivial. It's always actually unit. And on its own, this is very boring. Of course, if we just wanted a type which was the unit, we had the unit lying around. But the important bit is that top was part of this big category at the beginning. And there were equations that related top to other things in our nest of modalities. So in particular, we had an equation that said evaluating at 0 of later of A was top of A. But we've just said top of A was the unit, which means that finally, evaluating later of A at 0 is now trivial. The thing is, I'd like to show the rule at this point, which makes this true, but I've discovered as sort of a matter of practice that if you try and give a talk on modal type theory and you start explaining how modal type theory works, that will be the only thing you talk about. And I don't want to talk about that the entire talk. So you can see the paper if you want to see the gamma and turnstile rules. Okay? I'd rather focus on the consequence of this rule, which is a lot more types are accessible. In particular, the existence of top, together with its interactions with other modalities, and this new rule tells us that accessible types are closed under later, and every constant type is accessible. So in particular, 0 plus bool and nat are all accessible. And so on the previous slide, we had all of the negative types in the universe, and now on this slide, we have all of the positive types. And so the consequence of this is that we can take normal guarded type theory with all the normal operations, normal connectives, Martin-Love type theory, that sort of thing, and interpret it into Gatsby and compile Loeb induction in that standard guarded type theory to our definable version of Loeb induction. And in particular, a user basically never encounters a non-accessible type. They do exist, they just don't come up as much. And the consequence of that is that when you're programming in Gatsby, you just get to kind of pretend Loeb induction exists. And you get to never talk about BOM in particular. So that last claim is something that one has to test a bit, that when you actually use Gatsby, it's, you don't end up manipulating the bomb proposition yourself. Ideally, this is the part where I'd say we have an implementation of modal type theory, and I tested it in Agda, but we don't have an implementation of modal type theory yet that's sufficiently flexible to support all these modalities. And so instead, we have LaTeX. So I've carried out some pen and paper case studies and redone some of the classical results from guarded recursion, step index logical relations, co-inductive types, and I found it to be a highly usable system. All right, so for the sake of time, I'm going to skip forward here and just say that that was Gatsby. So it is a new approach to guarded recursion, which is modality-centric. We had a lot of modalities. We had one new principle about those modalities, that top of A is unit, and from it, we derive the essence of guarded recursion and loop induction. Thank you.
We've already got a lot of questions. I see Bob.
Just a quick clarification. Did you say you have a whole class of inductive types, or you just listed specific ones? I wasn't sure. Like you have an inductive type constructor of some class of inductive types that you can do?
Any inductive type which doesn't use, so any inductive type in standard type theory will lift to an accessible type. If you start invoking other guarded types, then it becomes more subtle, but it's still closed under a lot of operations. Yeah, like you can have lists. Everything is okay. Yeah.
Do we still have a question over here? Same question. Same question. More questions. So while the next speaker sets up, I'll ask you to do something that I think you might have had a backup slide for, so sorry about this. Can you say more about the meta theory of your system?
Right. So let me unplug here. So of course, the big question is whether Gatsby also satisfies normalization and canonicity. And the thing is, because it builds on cubical type theory and modal type theory, this is quite an intricate theorem. So what we can prove is that modal type theory sans the cubical stuff with this new rule satisfies normalization and canonicity. That's fine. The issue is that in order to prove that the entire system does, we also need to integrate univalence in a computational way. And this involves fusing two very intricate proofs. So future work is to show that the actual total system, the fusion of everything, works. All right.
Great. So let's thank the speaker again.